In this lecture, we're going to be talking about our final topic for Chapter 17, which is energy calculations. This is the final topic for the electrochemistry chapter. And to do these kinds of calculations, you just need to really master a bunch of fundamental definitions, and then really it comes down to a matter of unit conversion. So these definitions I want to start with are defining what charge is. You can think about charge as the kind of amount of electrons. And the way that we can kind of interconvert between the amount of electrons and charge is using the Faraday constant that I introduced in a previous lecture. And that constant tells us the amount of charge on a mole of electrons. So it's 96,500. 9.65 times 10 to the 4 coulombs per mole of electrons. So coulombs are the units of charge, and you can kind of turn electrons into charge using the Faraday constant. All right, another key definition that you need for energetic calculations is the definition of current. Current is simply the amount of charge per unit of time. That's all it is. So the units of current are coulombs per second. The SI units of current are coulombs per second. Now, 1 coulomb per second is referred to as 1 amp. An amp is often abbreviated with just a capital letter A. So an amp is a coulomb per second. So amp is a unit of current. It is synonymous with coulomb per second. And it's simply the amount of charge per unit time. Energy. When we are asked to calculate energy, like the amount of energy we need to run an electrolytic cell, we take the charge and we multiply it by the electrochemical cell potential. Charge times potential equals energy. The unit of energy you are familiar with. It's a joule. The unit of charge is coulomb. And the unit of electrochemical cell potential is volt. So here we get the relationship where 1 joule equals 1 coulomb volt. So you can interconvert between charge and potential and energy. The final definition that I want to give you guys is power. So there's an old joke in physics, watt is power, because power is typically expressed in units of watts. Power is the amount of energy per unit of time, and its unit is watt, and 1 watt is equal to 1 joule per second, because you're dealing with energy, which has a unit of joule, over time, which has an SI unit of seconds. Another way of thinking about that, so power is also equal to, you can figure this out by just taking everything that I've said above, is current times potential is equal to power. So current times potential, the unit of current is amp, potential is volt. So 1 amp volt is equal to 1 watt. All right, so how is this going to be useful to you? In this chapter, for the calculations that you're expected to do at the end of the chapter, you can actually convert from the amount of mass of a given chemical to the number of moles of electrons that get transferred as you change it in some kind of redox reaction. And from there, using the Faraday constant, you can get charge. And from charge, you can go to current if you have the unit of time. And then you can also figure out the amount of time that a reaction might take. And time, of course, is related to power. And power is related to energy, because power is just the amount of energy per unit time. And from energy, you can interconvert with charge, et cetera, et cetera, et cetera. So the problems you'll notice are just kind of fancy unit conversions. Let me give you an example of a problem like this. Take this reaction a redox reaction where we have two iron 2 pluses in aqueous solution and cobalt 2 plus in aqueous solution. And we are combining these to reduce cobalt 2 to cobalt 0 and plate it out as a solid. In the process, iron 2 plus gets oxidized to iron 3. So, taking this example, I want us to imagine that we're using a current of 0.050 amps for 250 seconds to plate out cobalt metal. So you want to basically use this reaction to synthesize cobalt metal. With that information, can we calculate the cell potential, the energy that this process takes in that 250 seconds, the power in watts, and the mass of cobalt produced in those 250 seconds? So this is really just a fancy unit conversion, except for the first aspect, which is to calculate the cell potential. To calculate the cell potential, you need to use the standard reduction potentials from the table. So that one is going to be taking, let's see, minus is going to be, all right, you can take the cell potential of the cathode and subtract the cell potential of the anode to get, and these are just values from the standard reduction potentials, minus 0.28 volts, minus 0.77 volts, and that will give you an electrochemical cell potential of minus 1.05 volts. So that's the first quantity you were asked for, the voltage or the potential. You are also asked for the energy. Okay, so what's energy? Let's go back to my definitions. Energy is charge times potential. I just calculated the potential, so now I need to figure out the charge. Charge is in coulombs, and I have the current. So I have the current in amps. That was given to me in the problem. And it's important here to remember that amps are synonymous with coulombs per second. So if I want to calculate the charge, I can take the number of amps, which is really just coulombs per second, and multiply it by the number of seconds that I'm running this reaction for to get the charge, which is just in plain coulombs. Okay, so if I do this here, the seconds cancel and I'm left with coulombs. Energy now is going to be multiplying the charge times the potential. So remember, energy is in joules, and a joule is a coulomb volt. So I need to take the charge and multiply it by the potential, 1.05 volts. You could leave the negative in there. It doesn't really matter, but you'll get 13.1 coulomb volts. Oops. 13.1 coulomb volts, which is really just 13.1 joules. Okay, and this is the amount of energy that you would have to put in to this reaction to make it go. So I would put this as a positive quantity, because if the voltage is negative, then you need to put this energy into the electrolytic cell to make it go. So really the signs should be reversed for voltage and energy. Okay, so that's why I have a positive sign here. You have to think about this, right? If you have a negative voltage, you have a reverse spontaneous reaction, your energy, like a delta G type of energy, would have to be positive. Power is just the amount of energy per unit time. So that would be 13.1 joules per 250 seconds, and that would equal 0.050 watts. or the power of this process. So I think, what do? We calculated the energy, we calculated the power. The final thing that we need to calculate is the mass of cobalt that are produced in these 250 seconds. So the easiest way to convert between charge and mass is to use the Faraday constant. So I would take this charge and use the Faraday constant to convert it to the number of moles, and then that's going to set us on a path to get the mass of cobalt. So to get the mass of cobalt that's plated out in this electrolytic process, I would take 12.5 coulombs, which is the charge that we calculated, and then take the Faraday constant. I'm going to flip the Faraday constant over, so I'm going to multiply this by its reciprocal. And that will basically take that charge and convert it to moles of electrons. So I'm on the way to kind of converting it to a mass. Now, how many moles of electrons are transferred in this reaction? Let's take a look at the reaction. It is a 2-electron oxidation, a 2-electron reduction, rather. Cobalt 2 plus is being oxidized to cobalt 0. So I have 2 moles of electrons transferred in this reaction. So I am going to get 1 mole of CO0 plated out for every 2 moles of electrons that I transferred. And I want the mass, so I need the